right. Hey, everybody. Welcome back to another lesson in AP Calculus. Today, we're going to be talking about the mean value theorem for integrals and the average value of a function. So, yeah, that's right. I told you the mean value theorem was important, and here it is again, because it is important. So, the mean value theorem, you're probably most likely you're familiar with this version here, that on a continuous closed interval that is differentiable in the open interval a to b, that there exists some value c where the derivative is equal to the average rate of change, or the slope of the secant line from a to b, which is found from saying f of b minus f of a over b minus a. Now, that's the way we typically learn it. You might recall, though, that there is an important alternate version of that. If I multiply both sides of this equation by b minus a, I get this statement here. Which is nice because it doesn't have a fraction bar in it. But it has another important part, so let's hold off on that. So we're going to use this form here, this kind of one-line version here, that f prime of c times b minus a is equal to f of b minus f of a. Now, let's also review the fundamental theorem of calculus. Technically, this is part 2, that if f is continuous on a closed interval from a to b, then the integral from a to b of f prime of x dx is equal to f of b minus f of a. Well, now you'll notice that these two theorems have something in common. They have an f of b minus f of a. So with simple substitution, we can conclude that if f is continuous and differentiable on the intervals required by the mean value theorem, that we can say that this must equal this. So we can say that f prime from a, the integral of f prime from a to b is equal to f prime at some value c times b minus a. Now, the primes, though, are usually not written when we express it this way. So there's no real reason for me to say f prime here and over here, because it just means they're on the same level of integration, or differentiation, you might say. They're not one higher than the other. So you could call it f double prime and f double prime, but they're the same. So we usually say the integral from a to b of f of x is equal to f of c times b minus a. And that's exactly what the mean value theorem for integrals is saying. This is we call it the mean value theorem for integrals, but it's still part of the mean value theorem. Now, the geometric interpretation of this mean value theorem is that for a positive function f, if let's just stick with positive, it'll make it easier, there's a number c between a and b such that the rectangle with base AB and height f of c has the same area as the region under the curve from a to b. Let me demonstrate what I think that would look like. So if I have, let's say this is f, and we're going to let f go from a to b. Okay, we're going to look at the integral from a to b. Well, the integral from a to b there is this area here, okay? What the mean value theorem is saying, and if I can possibly, a big if here, if I can kind of recreate the graph I drew over there, I probably should have cut and pasted it first, but the mean value theorem is saying that somewhere on this interval from a to b, that there's some magical number c. And we're used to this magical number c where the tangent line is equal to the slope of the secant. This is a little different. We're going to say that there's some height, and it could happen more than once. Looks like this time it might happen more than once, if this is my guess, where this c value here, where if I take it up to the curve, that f of c times b minus a, this f of c times b minus a, f of c is your height, b minus a is your base, it makes a rectangle that has the exact area. It's like a Riemann sum of one interval, but we've chosen our point, not left endpoint, right endpoint, somewhere in the middle, we've chosen our point so perfectly that our Riemann sum of only one interval is actually equal to the exact area underneath the curve. That's that f of c. And we're going to call this f of c, we're going to call this the average value. It's the average value for the function. And so that brings us here. So the average value is simply dividing both sides by b minus a here gives you this average value. So the average value function is really just rewriting of the mean value theorem for integrals. So a couple of warnings with the average value. Be really careful about it because you need to make sure that it's asking for average value and not average rate of change. Okay? And average value is not always sound like average value. Because if your function is a rate of change, like a rate of flow, it might say, what is the average rate of flow? And you may think, oh, well, that's a rate, average rate, that's average rate of change. Well, no, not necessarily. If the function you have is a rate, then it's just average value. So you just got to be real careful paying attention to the difference between average value and average rate of change. And hopefully we'll have enough chance in this course to see several of those questions kind of juxtaposed next to each other to see the difference. So there it is, what I call my favorite function, fave. 1 over b minus a times the integral from a to b. You simply take the integral and divide it by the width of the interval. So given this function f of x, let's find the average value of f on that interval. So we're going to find the average value of f from -1 to 2. Well, that's fave, f average, right? Get it? Is equal to 1 over b minus a, so 2 minus a -1, times the integral from -1 to 2 of f of x dx. Well, let me go ahead and just put in f of x. So that's 1 plus x squared dx. All right, well, 1 over 2 minus a negative, that's plus a positive, so that's 1/3 times, let's go ahead and integrate, actually. We'll put the little thing there. This is an easy integral to take. X plus x to the third over 3 from -1 to 2. So this becomes 1/3, and I'm going to plug in the 2. I get 2 plus 8/3 minus, I'll plug in the -1, -1 minus 1/3. And we have some simplifying to do here. If this was a free response question, I'd probably stop right here. But let's go ahead and simplify it. This is, let's see here, 6/3 plus 8/3 is 14/3. And this is, in here we have -1/3, -1 minus 1/3, that is a -4/3. So I have minus a -4/3, but it ends up becoming plus a positive. So this becomes 18/3 times 1/3, which is 18/9, which is 2. So 2 is the answer that we get. 18/3 is, 6. So 2 is apparently the average value of that function. So let's find the c value that results in the fave equaling f of c. So we know from the mean value theorem that there must be a value c that actually that would actually have this average value. I mean, it makes sense. If it's the average value, we would expect there to be an x value that has that value, since we're saying it's the average. But it does require continuity for that to exist. So let's find it. We're going to say, when does 2 equal 1 plus x squared? Well, this is not a difficult algebra problem. We get plus or minus 1 is equal to x. So -1, though, is on these endpoints. That's not what the mean value theorem says. The mean value theorem says it should exist on the interior. So the value that we're guaranteed is the positive one. So that's the value guaranteed by the mean value theorem. All right, so let's take a look at the sketch of these two. So we were looking at f of x equals 1 plus x squared, and we were looking at an interval from -1 to 2. All right, well, let's see here. Let's do -1 over here, and maybe positive 1 here, and positive 2. And we'll go up to 1, 2, 3, 4, 5. So when x equals 2, the y value is 5. X equals 0, it's 1. At negative 1, it is 2. So the curve looks kind of like that. We know the shape of we know the area would be this, the integral is this area here, but what we found was that at positive 1, if we drew a rectangle that went through the height at x equals 1, we would get an absolute perfect rectangle. That's area, this red rectangle is equal to the area under the blue curve. And I think, my drawing is not perfect, but I think it's probably, the right answer. It looks pretty good to me. All right. So I've got a practice problem for you to do. I want you to answer A and B, please. All right, let's see how you did. A says use a left Riemann sum with 3 subintervals to estimate the average value of f on the interval from 5 to 17. So we're going to get the average value. So we're going to look from 1 over 17 minus 5, from the integral from 5 to 17 of f of x dx. That's simply the average value. So that's 1 over 12 times, we're going to be using a left Riemann sum, and 3 subintervals from here to here to here. So this has an interval width of 4 and a height of 23. Excuse me. This is a width of 3. And we're using our left endpoint, so 29. And this here is a width of 5. And we got a height of 36. Okay? And we could add all that up and figure out what it is. If you're interested, I'm happy to throw that into a calculator right quick. We don't have to, though, unless it's a multiple choice question. We know that we don't have to evaluate these things. We probably would make sure we use the proper units if there's units in this problem, but there's not. So 4 times 23 plus 3 times 29 plus 5 times 36 is 29.917. There we go. Notice that because we're multiplying by these different intervals, it seems like, the length of time in x that a value is in at 29 or something like that, that plays a big difference in how these things work out. So it's really averaging it out on the table. If we're going to get a different average if we made this value from like 12 to 17 even longer, it's going to pull it more towards this 36. So just think about how that would work out. All right, let's find the average rate of change of f on the interval from 5 to 17. Okay, good. So we've been asked the 2 different things here. So here was the average value. Now we want the average rate of change. The average rate of change formula is f of b minus f of a over b minus a. So f of 17 is 27, f of 5 is 23, 17 minus 5 is 12. So this ends up being 4 over 12, or 1/3. That's the average rate of change. All right, let's go to the next question. All right, a study suggests that between the hours of 1 and 4 on Wednesday, that the speed of traffic on a certain freeway exit is modeled by this function, where the speed is measured in kilometers per hour and t is the number of hours past noon. Find the average speed of traffic from 1 to 4 p.m. All right, pause the video and give it a try. All right, let's see how we did. Got a calculator simulator here. We got to find the average speed. Well, we've got a function here for speed, right? So we're going to take the integral of multiplied by 1 over the difference in time here is 3 hours. And we're going from 1 to 4. How is t is the hours past noon? So 1 would be 1 hour and 4 would be 4 hours. Good. Of 2t cubed minus 21t squared plus 60t plus 20 dt. Now this would not be difficult to do without a calculator, probably. But let's practice entering in the calculator. It's always good to practice taking a numeric integral. Very important. All right. So what we're going to do is we're going to simply do 1 divided by 3. 1 over 3 times the integral of 2t cubed minus 21t squared plus 60t plus 20, I think was what it was, right? 20, yeah. And we're going to be integrating with respect to t, and we'll be doing it from 1 to 4. And we always want to hit diamond enter and make sure that we, or you can set your mode to approximate and make sure that our pretty print looks correct. So 65.5. And I bet that's actually the true value, but I'll double check just by arrowing up and hitting enter. Yeah, well, yeah, I think we can say for certainty that's. But I'll say that if you want me to say 3 decimals, just to be careful. So that's kilometers per hour. That is our average speed. All right. Got another practice for us. We got, suppose that during a typical winter day in Minneapolis, the temperature in degrees Celsius, X hours after midnight is shown in the graph. I want you to use a right Riemann sum of 4 subintervals to find the average temperature from 4 a.m. to 8 p.m. I like this question. I don't really like the graph, so be careful with it. The y-axis is counting by 2, and so is the x-axis. So just be aware that they're counting by 2s, okay? All right, and then pause the video and give it a try. Okay, let's see how we did here. We're going to use a right Riemann sum of 4 subintervals to find the average temperature. So this is a function of temperature. So the average temperature is 1 over 8 p.m. to 4 a.m. So that is a difference of, 8 p.m. is the 10th is the 20th hour of the day. So this here is 8 p.m. So it's basically saying 20 minus 4, which is 16. We're going to integrate that. So from 4 to 20 of, I'm not sure what the name of this function is, so let's call it y of x dx. And we're going to be doing 4 subintervals. We're going from 4 to 20, and we're going to be using a right Riemann sum. So from here over, that's going to be 1, 2, well, that's not enough. That's not wide enough. I think I have to go all the way over to here. And then this next one we can take up to here. And then here. And then lastly, we come all the way over here. So this area here is a length of 4. So we have 1 over 16, and then we have a width of 4 times a height of, it's going down, so we'll put our negative, this is 2. So I'm going to say -1. Let's just estimate the -1, okay? Plus, again, 4 times, this time the height is 2. Bring it down here, plus 4 again. This time it looks like a height of 1. And then we'll do 4 again, but this time we're at a height of looks like -5 even. So we could add all that up. That's -4, +4, 8. So 8 minus 20 is a -12. So 1/16 times a -12 is equal to -3/4 degrees Celsius. That's our estimate there of the average temperature. We're going to estimate the times when the average temperature occurred. So the average temperature appears to occur, somewhere around here and here. So, around, see here, 4, 6, I'm going to say around 7 a.m. And so this is 2 p.m., 4 p.m., 6 p.m., and, well, I think a reasonable guess is around 7 p.m. So, yeah, it's probably a little bit earlier than that, though, because this is 2, 4, 6, yeah, maybe 6:30. Actually, I'm going to say that. I'm going to say 6:30 a.m. and 6:30 p.m. But around similar times in the day. But, just on two different sides of noon. All right, let's do another one. So pause the video and do practice A and B. All right, let's see how you did. We need to find an estimate of the volume of gravel in the pile after 24 hours using a midpoint Riemann sum of 3 subintervals. So gravel is loaded into a pile over a 24-hour period. The rate at which gravel was delivered, R of t, is shown in the table below. At time t equals 0 is 100 cubic feet of gravel in the pile. Estimate the volume of gravel in the pile. So we're going to start with 100, right? There's 100 cubic feet, and we're going to add to it all of the rate that it was added. Basically, we're going to add the amount that was added each hour for the number of hours that it did it. So we're going to go from 0 to 24, and we're going to be doing R of t dt. So that's going to be 100 plus, we're going to be using a midpoint Riemann sum. Yes, that'll be one interval, that'll be an interval, and that'll be an interval. And because it's a midpoint, I'll be choosing the y values are the R of t values based on those numbers, the midpoint between the interval. So it'll be 8 for the width from 0 to 8 times 8.8 plus 8 times 9.2 plus 8 times 8.1. And that is going to be the amount of cubic feet of gravel. And that is after 24 hours. That's how much is in the pit. It says approximate R prime of 10, use proper units to describe the meaning of this value. Well, R prime of 10, that is, we can estimate that by using the slope of the secant line around it. So I'll use R of, looks like 12 over R of 8 is our best, sorry, not over R of 8, minus R of 8 over 12 minus 8 is our best bet. So 9.2 minus 9.1 over 12 minus 8, that is 0.1 over 4. And the units is in cubic feet per hour per hour. Remember, when you take a derivative, you do the y units per the x units. What does that mean in terms of this situation, though? Well, the meaning behind it is that at t equals 10 hours, the rate of gravel delivery is increasing by 0.1 over 4 cubic feet per hour each hour. All right, next we're going to use a midpoint Riemann sum of 3 subintervals to estimate the average rate of gravel delivery over 24 hours. The average rate, we were given rate. We were given a rate function. They want an average rate. That's our fave function. So the average rate average, over the 24 period, so 1 over 24 minus 0 times the integral from 0 to 24 of R of t dt. So that's 1 over 24 and times, and it's going to be basically, once again, using these things here because it's another midpoint Riemann sum. So we'll just do all of that. And that average rate, the average value of a function has the same units as that function. So it's going to be in cubic feet per hour. Last, it says find the average rate of change of the rate of gravel delivery. That means over those 24 hours. That's the average rate of change of it. Then we got to do R of 24 minus R of 0 over 24 minus 0. That's a totally different thing. So the average rate of change would be 6.5 minus 8 over 24 minus 0, and the units is just like the derivative, cubic feet per hour per hour. So over the 24-hour period, whatever that number is, that's the rate that it will looks like it's decreasing in gravel delivery. All right, well, that's it for this lesson. I'll see you in the next one.